Okay, so we're monitoring the patient, and we've got a 233 coil well, that's okay. 233 coil thing, conductor, and we get a delta area of our coil of 39.0 centimeters squared. So each coil increases by this much. So our actual delta area, I'm going to call this coil. So our delta area is N delta A coil, as we have a number of turns. And our B field is 50 microteslas, and it's at an angle of 28 degrees with the plane of the coil. So that's 28 degrees. Now, when we calculate our phi, it's B dot A, and our A vector is actually perpendicular to the plane of the coil. So we really need this angle in here. So our theta is 90 minus 28, which is 62 degrees. So then our flux is B a cosine of 62 degrees. Now we want EMF, so that's d phi by dt negative. We want average, and we've got a full time, so we're just going to turn this into deltas. So delta phi over delta t. Our B field isn't changing, so our delta phi is just B cosine of 62 degrees times delta A over our delta t. And we're given, and as I said above, our delta A is just N delta A coil, so this is going to be minus B cosine of 62 degrees N delta A coil over delta T. So now we have everything we need here. So our B is 50.0 times 10 to the minus 6 Tesla, cosine of 62 degrees, N turns is 233. Delta A coil is 39.0 centimeters squared. We're going to need to multiply by 1 times 10 to the minus 2 meters per centimeter squared to get the units proper. And then our delta T is 1.80 seconds. If we work this all through on our calculator and do it all right here, then we'll get minus 1.185 times 10 to the minus 5 volts. Or our magnitude of our EMF is just 11.85 times 10 to the minus 6 volts, or 11.85 microvolts. Checking the solution here. I'm going to plug this all in. So that looks okay. The answers do differ by quite a bit, but then if we look, They use 200 for the number of turns, not 233. So I don't know if this question was edited at some point, but in any case, the number of turns used in the solution, 200, should be 233. So I'm just going to say it's incorrect.